So in this video, I will be trying to solve another previous year problem from KTU. So this 2019 scheme problem. This was asked in 2020 December for 8 marks. This is from module 5. In module 5, this is from the column section. The question is, a short column having length of 0.5 meter and made of solid aluminum rod of 25 mm diameter is pinned at both ends. So it's a very small column. Determine the Euler critical load for the column. In order to reduce the weight of the member by 25%, the cross section is changed to hollow circular section of 25 mm external diameter. Determine the critical load of the modified column. Also determine the percentage reduction in critical load due to cross section modification. Take E equal to 72.8 GBA. Okay, so we'll solve the first portion first. So the length of the column is given. So in column problems, the first thing that you have to draw is the boundary condition for the column. Okay, what is the end condition? So this here it is telling it's pinned in both ends. It is pinned in both ends. So total length is given as 0.5 meter or I will say 50 mm. So it's a very small short column. Okay, so that means effective length is nothing but 50 mm. Since the both ends are pinned, effective length is same as the original length of the column. So this I hope you are familiar with. If it is fixed, it will be half of the length. The different boundary conditions, there are different lengths. I think I have done a previous problem regarding that. You can check that out. Now the diameter of the rod is given as 25 mm. It's a solid circular rod. 25 mm is the diameter. It is aluminum. They are telling it's aluminum. E is 72.8 GPa. So that means 72.8 into 10 to the power 3 MPa. Okay, this is what is given. We have to use Euler critical load formula. So now Euler critical load formula, I hope everyone is familiar with. Otherwise, you have to learn this formula. P is nothing but the crushing load or the crippling load, not crushing load. The crippling load is given by pi square E I upon L E square. Now E is given, pi is a constant, I we have to find. So for solid circular sections, the I value is given as pi upon 64 d to the power 4. So that is d to the power 4. So I will use this as capital D, d to the power 4. Okay, so this is the capital D. So this comes out to be pi upon 64 times 25 to the power 4. Right. So this is the critical load. Now what they are asked is, they are not asking the value of the okay, they have asked for the value of the critical load. So we'll calculate that. So this is equal to, so let me take out the calculator. So pi by 64 times 25 square, 25 raised to 4. So this, sorry. So this is 19174. 19174 mm to the power 4. This is the value of I. Now we just have to substitute these values to get the value of crippling load. That is pi square, E is 72.8 into 10 to the power 3. I is 19174 mm to the power 4. L is 50 square. So this gives me, so it is 50 square. 50 square. So this gives me, so just we'll calculate that very fast. Pi square times 72.8 times 1000 times 19174 divided by 50 square. So this is 5510662. 5510662 Newton, or nothing but 5510 kilonewton. So this is the crippling load. It's a very high value. This is what, so it's a very short column. So this may not be the actual strength of the column because it's a very, very short column. But nevertheless, this is what they have asked for. Now, there is a second part to the problem. The second part is they are telling instead of to reduce the weight, the weight of the column. It's a solid column. Weight could be a good value. So to reduce the weight of the column, what they have done is they have removed some portion from the center. Okay, how do I know it is removed from the center? So it is telling that the cross section is changed to a hollow circular section of 25 mm external diameter. So the diameter is keeping constant. They are removing some portion from the center. Okay, so they just removed some portion from the center. So it has become like this. So this has become this. Now external diameter is known. It is same as 25 mm. Now internal diameter, we don't know. We don't know the value of internal diameter. But one relationship that we know, it is basically what they're telling is from here to here, the weight of the column must reduce by 25%. Okay. So assuming that the weight of the solid column is 25%, is W. Let's say W is the weight of solid column. And density be rho be density of the material, density of aluminum. Okay, then W is nothing but area of the column, so I'll call this A1 into length of the column, which is original length 50 mm, into density of aluminum. This is the weight of the solid column. Now the weight of hollow column is, so this I'll call as A1. The weight of hollow column is reduced by 25%. That means the weight of hollow column is nothing but 0.75 times W. So weight of hollow column will be 0.75 W. So the total weight, if it is 1, 25% of the weight is removed. So the remaining weight will be, so 24th is 1/4. So remaining 3/4, that is 75% of the weight will be. So that is a 0.75 W. Okay. Now, so that means 0.75 W will be equal to area of this column. I'll call this A2 into the length of the column is same and density of the material also will be same. Okay. Now we will equate this. That means 0.75 A1 L rho equal to A2 L rho. Now L rho I can cancel. So that means second area should be 0.75 first area. So second area is area of the hollow section. So hollow section cross section area is nothing but pi by 4 into capital D outer diameter square minus inner diameter square. This will be 0.75 times pi by 4 into, now capital D is same, so I will use the same diameter D square. Okay, because capital D outer diameter of this, or diameter of this, is nothing but the outer diameter of hollow section. So that is why I am using the same D here. So pi by 4 I can cancel out. What is remaining is D square minus, or what I would say, yeah, D square minus D square is equal to 0.75 D square. So this gives, D square. This gives me, this I will take this side and this I will take this side. So that means small d square is equal to capital D square minus 0.75 capital D square. So this is the d square into, this means d square into 1 minus 0.75. I will take the d square common. D square into 0.25 equal to small d square. I will take the under root on both sides. So that means square root of both sides. That means d equal to d into root 0.25. So under root of 0.25 is nothing but half. Okay, 0.5. So that is small d is 0.5 times capital D. So capital D, as we know, it is nothing but 25 mm. So small d internal diameter is 0.5 times 25 mm. So that is 12.5 mm. So we got the internal diameter of the section. Now it is simple, same formula we have to apply. This is nothing but 12.5 mm. Okay. Now we can calculate the I of the section. I of hollow cylinder is given by pi by 60. Hollow section is given by pi by 64 into capital 2 d raised to 4 minus small d raised to 4. So this is nothing but pi by 64 into capital D is 25 raised to 4 minus small d is 12.5 raised to 4. So we'll just calculate this value fast. So this is pi by 64 times 25 raised to 4 minus 12.5 raised to 4. So this is 17976. 17976 mm raised to power 4. Okay. Now for hollow section, Euler's buckling load. For hollow section. So again same formula. So this I'll use P2 or I'll say P hollow. This is nothing but same formula, pi square E I hollow upon LE square. Okay. Now the critical load of this is nothing but pi square into E has been changed. What is the value of E? It is 17976. 17976 into I, sorry, not E, I has changed. This is I am sorry. E is same. It is 72.8 into 10 to the power 3 divided by LE is 50 square. Length is also same. Effective length is also same. So this comes out to be, so we'll just quickly calculate this also. So pi square times 17976 times 72.8 times 1000 divided by 50 square. So this gives me 5166354. 5166354. 6354 Newton. So that means it is 5166 kilonewton. Okay. So this is the new buckling load. Now also find the percentage reduction in critical load due to cross section modification. Now what is a percentage reduction? Percentage reduction is nothing but this minus this is the change. So change in strength. Change in P is nothing but 5510 minus 5166. So what is this? 5510 minus 5166. 344 kilonewton. Percentage reduction is 344 divided by 5510. So that is, so this divided by 5510 into 100. So this is nothing but 6.25%. So 0.0624 or 6.24%. Okay, so this when you write percentage reduction, you have to multiply by 100. So that is why it's 6.24%. So you can see, even though we have reduced 25% of the material, there is only 6% reduction in the strength. So it is always preferred, you can remove the material and, save some cost. So this saving of cost for 25% material will be a lot compared to the reduction in strength that we have. So basically the strength of the column has been reduced by 6.24%. So that's it. That's how you solve this problem. I hope this problem is clear. It's a direct problem. Only thing is this 25% could confuse some students, but otherwise it is a direct application of Euler's buckling formula. So that's all. Thank you. We will solve another problem in the next video.